Now recall that it is very similar, this Hamiltonian or energy is very similar to the energy of the Kepler problem. Do you know what the Kepler problem is?
I don't think I forgot. I think I've seen it before, probably.
Anyone else who has done classical mechanics?
I did classical, but I don't remember seeing this particular problem.
Well, it's a fancy name for. Do you know the history of Kepler? Have you heard of Kepler? Johannes Kepler, famous physicist and mathematician.
I mean, heard of him, but other than that, I don't know what he was famous for.
So very famous is Kepler's law is that Kepler was the first person to figure out that if you have a very heavy astronomical object, say the sun here, and and this is an empirical law, and there's a planet which goes around, the most general orbit of the planet is going to be an ellipse, okay? And suppose this is the planet, and the sun would be in one of the foci, right? So this is the sun. It'll be either in this focus or in this focus point. And the planet, if it's closer, it'll move faster. It'll move faster in such a way that the area that this sweeps out is, per unit time, called the areal velocity, is going to be equal to the area that it sweeps out in the same time when it's further away. So, meaning that the areal velocity is constant. Okay? So these two areas are the same. Okay? So the Kepler problem is just a problem, or it's a two-body problem. The gravitational two-body problem, okay? And it's very important not just in solar system, but also its relativistic counterpart is very important in, say, black hole mergers. When we do the computation of how much energy do black hole mergers give out in terms of gravitational wave, it's a very important problem. But what the Kepler problem tells us is that the combined motion of two bodies or two particles, and is consists of type 2 motions. One is the rectilinear motion, and it can be for any potential. The rectilinear motion of the center of mass. Number 2 is the relative motion of the two particles or the two bodies, okay? So which means that, it's just similar to saying that, okay, this is the solar system, but the solar system itself is moving with some velocity in our galaxy, right? So that is if you ignore the gravitational pull that the rest of the galaxy is putting on the solar system, which you cannot, but let's just put that, it affects it on a longer term, but on the shorter term, the motion of the whole solar system will look approximately rectilinear, right? So that's that motion, and then there's a motion of an individual planet around the sun. Okay, so these two motion can be separated. That's what Kepler's that's what Newton showed after he analyzed the Kepler problem. So to see this explicitly, what you want to do is that you want to start with R. R is going to be a vector which has big X, big Y, big Z. And this is going to be the position of the center of mass. So center of mass is M1, the position of the first particle, plus M2, position of the second particle, divided by M1 plus M2, right? So if you have some reference frame like this, and for the sun, of course, the center mass will coincide with approximately somewhere inside the sun, right? Because the sun is so big, the center of mass. So this would be R. And then there will be another vector which is going to give you the relative motion between the two particles, and that's, let's call it small r. And small r will have components small x, small y, small z, and that will be just r1 minus r2. Okay? So this is the relative positions, or the relative positions of the particles. Okay? Or position. Okay? Conceptually, it probably should make sense, but let's see. So we can now invert these relationships. If we invert it, then we can say R1 is going to be big R plus M by M1 small r, and R2 will be big R minus M by M2 small r. And this is, you need to show this yourself, okay? And M is going to be M1, M2 divided by, so M is not M1 plus M2, M is M1, M2 divided by M1 plus M2, and this is called the reduced mass. Okay. As you see that if one of the particles, if M1, say, its mass is infinite, so for example, for the sun, this is a good approximation in comparison with the Earth. Then M will become just M2. So, having, defined these things, it's also very easy to show, and, you just have to use the chain rule is the gradient or the nabla operator with respect to R1 is given by M by M2, the nabla R, plus the gradient operator of big R and small r. So small r, I'm not going to write this R. I'm just going to, okay. And then this is going to be M by M1 del R minus del, okay? So just this is going to be just d by dx. This is a differential operator, which is a vector operator. And this thing will be d by dx, the small derivatives with respect to the small x, y, and z. So if I now do this, then the Schrodinger equation becomes very easy to look at. We have a term which is minus h squared divided by 2 m1 plus m2. This is the total mass, say big M, delta R squared, the big R, minus h squared by 2m. This is the reduced mass, and then small del squared psi, and then minus e squared by r psi et of psi. So as you can see, we have one term which is giving you the motion of the center of mass. See that there is no potential which involves this r, right? So if you do a separation of variable, this is going to give you a free Schrodinger equation. So the center of mass is going to be the same as the center of mass Schrodinger equation is going to be the same as the Schrodinger equation for a particle, for a free particle. Whereas this thing is going to give you the Schrodinger equation for a particle in a spherically symmetric potential. So let's stop here, and in the next class, we're going to do the separation of variable and solve this equation, okay? Any questions? Everyone seems present except Nahi. Okay, any questions?
No, sir. No.
Are you guys done with all your other midterms?
No, there's still,
The 405 mid is like in 40 minutes, I think.
yeah, 7 o'clock. Then
Yeah.
optics will be on 16th, maybe, yeah, 16th.
Okay. All right, well, good luck with that. Are you guys worried about 405? Haha.
Well, not so much right now, so
Okay,
it's getting better.
okay,
It's
awesome.
probably gonna set in the moment we get the paper or something.
Okay. Okay. Anyway, good luck, and I will post the midterm on sometime in the morning of Friday, and then you'll have 24 hours. Okay.
Okay. All right. Thank you, sir. Goodbye.
Okay. Thank you.
Thank you, sir.